Okay, Assalamualaikum warahmatullahi wabarakatuh. It's about this chapter is about vapor liquid equilibrium. Okay, and this chapter is relevant to the separation process that you need to do the separation on the components. Okay, when you are given the mixture of components. Okay, so components involve species or any composition that you are talking about. So in our case, for distillation, we are only dealing with binary mixture, meaning that you have a mixture of component A and component B. And I believe that you have learned about your material balance. So now is the application of material balance is applied in this chapter. Okay. So the material balance is very simple because it does not involve reaction. Okay. So whatever that goes in the system go into the system will come out from the system. Okay. So that is our material balance. Very simple. Okay, so you know that. Okay, when we are dealing with distillation column, so this is a simple one. All right, simple schematic diagram. So you have distillate, you have bottom, you have feed. So whatever that you have for your feed that comes into the system, okay, after it goes into the process, that will come out from the system. Okay, so material balance only involve F is equal to D plus B. Okay, D plus B. But if you're talking about components, you have A component. So A component, normally you're going to collect in the system. So this will give you the component XFA, and then this is XDA, and then the bottom one is XBA. Okay, so when you do the material balance, so it's only involve a very simple one. So that this is overall material balance, and the other one is component A material balance. So you have component A material balance that will give you XFA multiplied by flow rates of the feed, which is equal to XDA A multiplied by the flow rates of distillate plus XBA multiplied by the flow rates at the bottom. Okay, for distillation, this is the material balance that you have to deal with. And remember that when you are given binary mixture, okay, binary mixture consists of A and B. This is binary mixture. Okay, right? So binary mixture A and B. Okay, so when you recognize what is A, what is B, then it's easy for you to solve the problem. Okay, so the boiling point of A should be lower compared to boiling point of B. Okay, so boiling point of B should be higher. Okay, so in your distillation column, you have at this bottom part, you have a reboiler. So that's why the composition of B will be collected at the bottom of the product. Okay, because only the lighter one will go through the top of the column. Okay, so that's why majority of the composition that you collect at the top product is always component A. Okay, component A. So component A, I just simplified here. The more volatile component should always equal to component A, where it has lower boiling point. Okay, where it has lower boiling point. All right. But if you look for component B, okay, component B, okay, it is less volatile. All right, less volatile because it has higher boiling point. Right, so more component will be collected at the bottom product for component B. So when you talk about the component, so remember you learn about mass uh, or mole fraction. Okay, mole fraction XA plus XB always equal to 1. Okay, so for distillate, you get XA more than XB. Okay, you get more XA, okay, component A. All right, so to make it easy, okay, let me put this way, sorry, to avoid the misunderstanding. Okay, so at your distillate, your XDA must be greater than XDB. Okay, all right. At the bottom, okay, at the bottom, you're going to have X D B, sorry, undo. X B A should be less than X B B. Okay, so you have to understand that. All right. Okay. Okay. Now let's proceed to the next one. Okay. Any question you should ask me. Okay. So your job is to know how to plot the equilibrium graph. Okay. To plot the equilibrium graph is to know uh, about the composition that you're dealing with. Okay. So you have this already. Okay. All right. So every temperature that you have will give you a pair of equilibrium data. Okay, a pair of equilibrium data. So each temperature gives you one equilibrium data, which is the value of X and the value of Y. Okay, the value of X and one value of Y. So they have a pair of equilibrium data for each temperature. So that's why for distillation process, you can have more than one uh, product stream, more than two product stream. All right, so that can be a fractional distillation. Okay, like how we distillate the crude oil, right, where you have a very different component of crude oil. Okay, so by having that, all right, okay, you should know how to use the Rod's law and Dalton's law. Okay, Rod's law and Dalton's law. A combination of Rod's law and Dalton's law will give you this particular equation. So whatever equation that you are given, okay, whatever equations that you are given, whatever questions that you have, if you were to find the value of X and Y, the value of X and Y, you can use any equation here as long as you have the data, okay, to solve the problem. All right. If you cannot use this one to find XA, find this one. Okay, find this one, no problem. Okay. If you cannot find YA using this equation, you use this equation. Okay. So definitely your job is to complete the curve. Okay. So your job is to complete the curve, right? So don't forget to draw the 45-degree line and the maximum area of the graph paper. Okay, maximum area of the graph paper. All right. So what is relative volatility? Okay, just to make you understand. Okay, all right. So this is only a revision. Okay, I believe that you have learned this with Madam Shahida. Okay, so relative volatility, the symbol is alpha. Alpha, eh? Okay, so alpha is the calculated value to determine whether you want to proceed with the separation process using distillation or you don't want to proceed. Okay, so alpha, the value of alpha is the indicator for you to proceed or not to proceed. Because in the factory, in the industry, you should have known before before you proceed with the process. You cannot just simply, okay, I want to use separation distillation to do the separation process. You cannot do that. So you have to determine first what should you do, what decision should you make before you proceed with the real process. Okay, so the value of alpha will give you the indicator. Okay, if you have a value of alpha, alpha is only a value. If you get the value of alpha, which is greater than 1, it is possible to do the separation process. If you get less than 1, you should not proceed with the distillation process because it will give you poor separation. So when you have poor separation, it will not meet the objective. Okay, so how to use that? Alpha can be used using this formula. Okay, or you can get your alpha from this formula. Okay, but same thing just now I mentioned about how are you going to have the equilibrium data. This is one way for you to get the equilibrium data. Okay, equilibrium data. Okay, with the known x, you're gonna know you're going to find out the value of y. With the known x, you get a value of alpha. No, with the known uh, with the known x, okay, when you know the value of x, okay, you know the value of y. Okay, right? So you can only use this equation to find the equilibrium data, okay, if you have alpha, where alpha should be constant in this case. Okay, when alpha is constant, what's going on? When alpha is constant, meaning that you are dealing with the ideal solution. Okay, ideal solution. So if the alpha is varied, if the alpha are varied, okay, you are dealing with non-ideal solution. Okay, non-ideal solution. Okay, so that is to determine type of solution. So focus, because in the exam, something they will ask you the questions that you know already, but you don't remember what you have learned because sometimes due to your lack of concentration in the class. Okay, so you should read your textbook. Okay. Okay. So I've given you the assignment regarding to the flash distillation. So this is flash distillation. Okay. All right. So focus on this particular flash distillation. Okay. All right. So your quiz will cover flash normally. All right. Okay. So you have to know the material balance. So I just remind you a little bit. So for flash distillation, this is the overall mass balance. This is component mass balance. Okay. So you're dealing with A, so you can just put XFA, XYA, LXA. Okay. So whatever it is, okay, you should know how to find the small f here. Okay. Small f here is determined by the ratio of ratio of vapor over the feed. Okay. So vapor the flow rate of vapor, you divide with the feed, you get the small f. With the small f, you need to substitute in this equation, which is called operating line. Okay, so operating line is very important in distillation. Okay, why? Because you need operating line to solve the problem. For each distillation column, you have different operating line. Okay, all right. So whatever it is, when you do the substitution for operating line, your job, most of your job is to look for the y-intercept. Okay, look for the y-intercept. Okay, because from the y-intercept, you should be able to solve the operating line. Okay. So we have done that already. Okay. All right. So this is the summary of your notes. Okay. Okay. The red line here is called the operating line. So OL. Okay. And the intercept here is the y-intercept, which is your C. Okay. Your C is actually equal to XFA over F. In the equation, that y-intercept is this one. Okay, so very important, every operating line, okay, majority of the operating line is based on the, is begin at the 45-degree line. Okay, 45-degree line. Okay, so any question? Okay, so let's say we use this graph, okay, to be your continuous distillation graph. Okay, so for continuous distillation, you should be able to draw the curve, the equilibrium curve, and the 45-degree line. Okay, so this is the shortcut. You need to know the mole fraction of your feed. Okay, the more volatile component of your feed. Next, you need to know, always solve this problem first. You need to know your distillate component for A, and also you need to know the component for BA. Okay, so this is your X, and this is the mole fraction of the liquid. Okay, mole fraction of the liquid. All right, so this is the job for you. Okay, so let's see, let's say the operating line for distillation come from enriching operating line, Q operating line, stripping operating line. Okay, so where do you get this line? Okay, these three lines. Penting, eh? Where do you get these three lines? Okay, look for the notes. Okay, you get enriching operating line above the feed. Okay, above the feed. So this section is called enriching section. The bottom part of the feed from the feed section is called stripping operating line, stripping section. So you get enriching operating line from this particular above section, and stripping operating line you get this below, okay, below this, which is SOL. While Q operating line you get from the feed, okay, from the feed level. So there are three operating lines. Okay, one you get above the feed line, the feed stream. Another one you get below the feed stream. And the third one you get on the feed. Okay, because Q operating line represent the condition of the feed. Okay, so we are talking about condition here. Okay, and EOL, we are talking about reflux ratio. And SOL, we are talking about vapor over liquid. Okay, proceed. Okay, all right. So you're going to look at this part. Okay. Okay, hold on. Okay, so this is how I simplified the diagram. Okay, so you have your reboiler, here, and then you have your condenser here. But this is a condenser. You only get reflux ratio when you have a recycle stream into the column. Once you collect the vapor at the top of the distillation column, you condense them, okay? And then you have two sections here. To the right is where you collect your distillate product, and to the left where you allow the vapor product to be fed into the column. And the reason is very simple: to increase the contact between the vapor and the liquid again and again until you get a very purified component A at the top of the column where you're going to collect at D. Okay, so the reflux ratio formula will use the formula where you have your Ln and D. Okay, so if I were to have this one, you're going to have your R is equal to Ln over D. Okay, so that's why when you have your reflux ratio, that will give you to use that information in enriching operating line. So for the feed, you have QOL. So that will represent the condition. Okay, the condition of the feed. Okay. So let's see what you have learned. Same thing, material balance that you have. Okay. And this is the operating line of EOL. Okay, whatever it is, you need to solve for your R. Okay, so that you can solve for the y-intercept. Okay, so this formula, so this one is your reflux ratio formula that I mentioned just now. Okay, so this one is in the form of y equal to mx plus c. So we need the c. We need this particular c. Okay, because when you have that c, okay, let me show you again. In the diagram that we have before. Which one is the sketch graph? Okay, so when you have your C, for let's say your C is here, okay, for let's say your C is here, which is XF, no, undo, which is your XDA over R plus 1. So this is your C. Okay, let's say your C is here. So since this is enriching operating line, you draw from here, okay, from XDA, okay, from XDA, you draw until you get this point, and then you just connect to the y-intercept. Okay, so this is not that nice. Undo. So let's say, okay, all right. Okay, for QOL, okay, now we go for Q pula. For Q, where do you get your Q? You get your Q from here. Okay, all right. So whatever given in this part is called the okay, the condition of the feed. Okay, so this is the condition of the feed. The feed can be in the form of saturated vapor. The feed can be in the form of saturated liquid, or the feed can be a mixture of liquid and vapor. So this is the condition. If they are given to you, then you have to know the value of Q. Okay, all right. So this Q operating line, Q operating line can be used when you have Q greater than 0 and less than 1. Can only be used for this one. Okay, right? So that Q operating line equation can only be used when the mixture is liquid and vapor. But if the feed is in the form of saturated vapor, the value is fixed. Okay, if it's in the form of saturated vapor, the value is fixed, which is Q equal to 0. So when the Q equal to 0, it just only a horizontal, it is only a horizontal line. Okay, when the Q is equal to 1, where the feed is in the form of saturated liquid, you can see it is only a vertical line. Definitely, it's begin at XFA. Yeah, XFA. So always begin at your 45-degree line, Q at the feed, so it's based on the mole fraction of the feed. EOL is based on the distillate, so it's begin from the distillate. Okay, and then B begin at the bottom, therefore you can, this is quite special case because you have 3 operating line, you have 3, enough to have 2 to solve for the third one, because all the 3 operating line will meet at one particular point. Okay, so if you have 2 of them intercept, then the other one will follow the same point to intercept. Okay, so if the Q is between 0 and 1, so you're going to get an incline, incline, all right, incline straight line, an incline line, okay, for your operating line. Because it is inclined, therefore, you need to solve this one to get the y-intercept. Okay, to get y-intercept. How to get the y-intercept? You just need to have to know this equation, and then let's say the y-intercept here. So just draw this one. Okay, so this is the y-intercept. that is actually equal to negative XFA over Q minus 1. Okay, where can you get the value of Q? That is another problem, kan? Okay, so how do you get Q? You get the value of Q for this operating line from the formula Q equal to percentage of liquid in the mixture, okay, percentage of the liquid in feed, okay, over, multiply, sorry. I give you the easiest way lah for you to calculate. Okay, so Q must be, you get your Q equal to percentage of liquid, okay, in the feed multiply with 1. Okay, multiply with 1. Okay, kenapa 1? Because Q equal to 1, the number that you use is 1. Q equal to 1 for saturated liquid, the multiplier is 1. Okay, the multiplier is 1. Okay, but for vapor, the multiplier is 0. Tapi kalau dia 0, tak perlulah. Nak darab dengan apa pun, dia tetap 0 juga kan? So, if you want to tambah lagi apa yang berlaku, ialah, okay, you boleh tambah kalau nak lah, tapi no need lah. Just use this formula. Okay, so that is Q. So I think you have drawn this graph already. You have drawn this equilibrium curve already. Okay, so from your graph paper, okay, you need to know the more volatile component in this case is benzene. Okay, the less volatile is toluene. All right, so benzene is your component A. Toluene is your component B. Okay, and then your distillate consists of 90 mole percent. So you have XDA, which is 0.9. Okay, and then the bottom part is given 10 mole percent of benzene. So XBA, I put A so that you understand. We are talking about only benzene here. Okay, and then your feed is consists of 50 more percent of benzene and 50 more percent of toluene. So we need only benzene here. Okay, we need only benzene here. Okay, all right. So when you have this information already, then you are given the reflux ratio in this question. So for the reflux ratio in this question, so you are given R is equal to 4.52 over 1 because it's given L over D already, Ln over D. Okay, so always rewrite the formula, okay, so that you understand what's going on. So this is only a portion. Flow rates of Ln is 4.52 parts out of 5.52. Yeah. So semua sekali ada berapa bahagian? Ada 5.52 bahagian, di mana 4.52 bahagian akan masuk ke Ln dan 1 bahagian akan masuk ke LD, dekat distillate. Okay. So if you were to separate the value, then it is based on this ratio. Okay, so meaning that Ln here 4.52 and then 5.52 parts, and then D will get only 1 part. The one part here represent the flow rates, flow rates. So jangan confuse. Okay. So you nak calculate the number of theoretical trace needed to use for the mercaptile method. Okay. So guna yang tadi. Okay. So when you do the graph, buat macam tadi, masukkan value dia, masukkan, ya. Masukkan. Saya nak semua orang faham hari ni, tak nak ada yang ketinggalan. Ya, tak nak ketinggalan zaman. Buat XD nanti berapa, masukkan XDA which is 0.9, masukkan XF, masukkan XFA, masukkan 0.5, XB, XBA, masukkan 0.1, and then draw the curve. Okay, nak tahu mana dia punya EOL, okay, EOL. So you need to start here and then cari intercept dia. Cari intercept C is equal to XD over R plus 1. Okay, cari from EOL equation. Okay, so this is EOL. Okay, and then you need one more line. Baca dulu ada apa-apa maklumat dekat sini. Okay, it's mentioned here. The condition of the feed is heating up to the saturated vapor. So saturated vapor, the Q value is fixed, which is Q equal to berapa tadi? Vapor Q equal to 0 kan? Q equal to 0 kat mana duduk dia? Vertical ke horizontal? Okay, based on the notes that you have, the saturated vapor, the value Q equal to 0, the line of your operating line should be a horizontal line, okay? Okay, for this question, when you want to draw the graph or using the graphical method, mercaptile graphical method, so what you need is to label the XB, the XF, and the XD, okay, which is XB is the mole fraction of the bottom product, XF is the mole fraction of the feed, and XD is the mole fraction of the distillates, okay. And then you also need to draw the enriching operating line. So to draw the enriching operating line, it begins at your distillate line, okay? It begins from your distillate composition, all right? And then you need the y-intercept of the enriching operating line. And then for this question also, you are given that the feed is at saturated vapor. So when it is at saturated vapor, the value of Q is equal to 0, all right? So when the value of Q equal to 0, this is a definite number. Therefore, when Q equal to 0, the Q operating line is only a horizontal line, okay? And for SOL, you're going to draw a line where you're going to extend the line until it meet the intersection between enriching operating line and the Q operating line. Okay, then you can start draw the stages to calculate the number of stages or theoretical number of stages. Okay, now what if the question asks you to calculate the number of theoretical stages for total reflux? So what you need is a very simple one, okay? Okay, for the total reflux, the information that you need is the mole fraction of the more volatile component for at the bottom product, the mole fraction for your distillate for the more volatile component, the 45-degree line, and the equilibrium curve. Okay, So using whatever that you have, the four information that you have, you can draw the stages. Okay, the reason is very simple. You don't need to draw the other operating line, such as enriching operating line, stripping operating line, or Q operating line, because the only operating line that you need is only a 45-degree line. And this is the how the graph looks like for total reflux.